Let's start with an interesting problem. We have to prove that in Budapest city there are at least two people out there with exactly same number of hair on their head. Now it seems like an absurd question, right? How on earth you're going to prove this? Some of you who are comparatively witty will be like, of course, in Budapest there are not only two people, there are lots of people out there who are completely bald, who has exactly zero number of hair on their head. Well, let's just leave the bald people alone. Even among the people who are not bald, there are at least two people who has exactly same number of hair on their head. Well, to be precise, there are actually at least 13 people out here with exactly same number of hair on their head. We are going to prove this, but before that I want to introduce you with a principle called the Pigeonhole Principle. Pigeonhole Principle is an extremely powerful tool in combinatorics, which is a branch of mathematics that studies counting techniques. Another name for the Pigeonhole Principle is Box Principle. Sometimes it is also called Dirichlet's Drawer Principle, named after mathematician Gustavo Dirichlet, who used this idea to solve some problems in number theory. Now, the inherent idea of the Pigeonhole Principle is very simple. You can understand it just by pure common sense. So let's see what the principle says. If you want to put more than n pigeons in n pigeonhole, then at least one hole you have to put more than one pigeon. This is the most elementary form of the Pigeonhole Principle. It is very easy to see intuitively why it's true. Let me give you a concrete example. Let's say I have 6 pigeons and I have to put those 6 pigeons among 5 pigeonholes. Now, even if I try to put only one pigeon in each of the holes, there will be 5 pigeons among 5 holes. So there is still one extra pigeon that I have to put somewhere. That means at least in one of the holes there will be more than one pigeon. The term pigeon or pigeonhole are just symbolic. We can replace them with any objects and boxes. Typical example of the implication of the Pigeonhole Principle are something like, let's say, in a group of 3 people, at least 2 people has the same sex, or in a group of 13 people, at least 2 people has a birthday on the same month, and so on. Now, some of you are probably thinking, oh, it's such a simple idea, why it's such a big deal? Well, believe it or not, with this simple idea you can solve some really difficult problems. You don't have to take my word for it. We will see some examples shortly. Let's start with the problem that we stated earlier. We're going to prove that in Budapest there are more than one people with exactly same number of hair. The total number of people in Budapest is approximately around 2 million. Now let's say 100,000 people among them are completely bald. So we're going to consider the remaining 1.9 million people who at least has some hair. On the other hand, the maximum number of hair a human being can have is around 150,000. Well, it differs a bit based on the hair color, but the maximum number of hair is around 150,000. That means the number of hair a person can have ranges from 1 to 150,000. We'll call each of these numbers the hair number. All the 1.9 million people in Budapest has hair number among any of these numbers. Now we're going to identify the number of hair as the boxes and the number of people in Budapest as objects, because we have to assign this 1.9 million people among this 150,000 hair number. So if we try to put 1.9 million objects in 150,000 boxes, we have to put more than one object in a box, as the number of object, in this case the number of people, is way higher than the number of boxes, in this case the hair number. To be precise, we have to put at least 13 objects in at least one of the boxes, as the number of objects is more than 12 times higher than the number of boxes. And that's it. We are done with our problem. Now let's see a bit more precise version of the Pigeonhole Principle. If you want to distribute kn plus 1 objects among n boxes, in one of the boxes you have to put at least k plus 1 objects where kn and both are natural numbers. You will understand it intuitively if you tinker around with it for a while, but we will actually prove it. The method that I will use to prove it is called proof by contradiction. I guess some of you don't know how proof by contradiction works, so I'll talk a little bit about it. If you already know, you can skip ahead. So let's say we want to prove that a statement P is true we are going to do is that we are going to assume that P is false and see what happens. If we proceed further, we will see that the consequence of P being false is something contradictory, something that doesn't make sense, something that cannot be true. That means our initial assumption that P is false was wrong. Therefore, P has to be true. So in proof by contradiction, we are showing that something is true by showing that it cannot be false. That's the whole idea. If we want to use this idea to prove our theorem, we're going to assume that if we want to put kn plus 1 objects among n boxes, we don't have to put k plus 1 objects in any of the boxes. Rather, we have to put at most k objects in any of the boxes. Well, that implies that the number of objects is at most k multiplied by n or kn, which doesn't match with the number of objects that we have, which is kn plus 1. That is a contradiction. That means our assumption that the theorem is false was wrong. That means our theorem has to be true. Now let's solve some fun and tricky problems using this red principle. The first problem that we have is prove that in a group of n people where n is greater or equal to 2, there are at least 2 people who has exactly same number of friends in the group. Side note is everyone in the group has at least one friend in the group. Now let's first see what is the maximum number of friends a person can have in that group. Well, other than that person, there are n-1 more people in the group. So the maximum number of friends a person can have is n-1. On the other hand, the minimum number of friends a person can have is 1, as it is given that everyone has at least one friend. So the number of friends a person can have ranges from 1 to n-1. Let's call this number the friends number. Now we have n people in the group. If we identify these n people as objects and n-1 friends number as the boxes, we can assign those n objects, in this case people, into those n-1 boxes, in this case the friends number. If we do that, then based on our pigeonhole principle, in one of the boxes there has to be at least 2 people. That means at least 2 people in the group will have same friends number or same number of friends. This completes our proof. Now let's solve a slightly trickier problem. 10 points are randomly chosen on a square with side length of 3 units. Prove that among these 10 points, there are at least 2 points whose distance between them is at most √2. At first, it seems like a geometry problem, right? To be fair, you will need some basic knowledge of geometry, but the main idea that you are going to use is the pigeonhole principle. Now the trickiest part in applying pigeonhole principle in solving any problem is to determine what will play the role of the objects and what will play the role of the boxes. Let's try to figure it out. We have to distribute 10 points on the square. So it is kind of obvious that these 10 points are our objects. What about the boxes? Well, to find the boxes, we are going to divide our square into 9 smaller squares. As the original square has a side length of 3 units, each of the smaller square has side length of 1 unit. Now if we want to distribute the 10 points among these 9 small squares, according to the pigeonhole principle, one of the square will contain at least 2 points. Now if we have 2 points on a square, the maximum distance they can have is equal to the length of the diagonal. Using Pythagorean theorem, the length of the diagonal in this case is √2. So the maximum distance those 2 points can have is √2. And we are done. I want to make a small remark before proceeding into the final problem. Instead of dividing the original square into 9 small squares, if we divide into 9 rectangles in the following way, we will not be able to solve the problem. Does that mean the pigeonhole principle is flawed? Not really. It just means that the box that we created were not appropriate. Pigeonhole principle doesn't give any information about the characteristics of the boxes or objects. It just tells us how we can assign the objects in the boxes. Finding the appropriate objects and the boxes is actually our task. The third and the final problem that we're going to solve is probably the trickiest. Prove that if we choose n+1 numbers from the set 1, 2, 3 up to 2n, one number out of this n+1 is divisible by another. It's not very obvious at first how we can apply pigeonhole principle here. We have to modify the problem quite a bit to make the pigeonhole principle useful here. Let's say we randomly choose n plus 1 numbers a1, a2, a3 up to an plus 1 and write them in the form ai equal to power k multiplied by bi, where bi is an odd number. We can express any integer in this form. If the number is odd number, we can write it as 2 power 0 multiplied by bi, which is the odd number. If the number is even, we can write it as power of 2 multiplied by the odd number. For example, we can write 5 as 2 power 0 multiplied by 5, 12 as 2 square multiplied by 3, 16 as 2 power 4 multiplied by 1, and so on. So we have n plus 1 odd numbers b1, b2, b3 up to bn plus 1 from the closed interval 1 to 2n minus 1. But there are only n distinct odd numbers in this interval. So if we assign those n plus 1 odd numbers into those n distinct odd numbers, according to the Pigeonhole principle, two odd numbers has to be the same. Let's say these two odd numbers are some arbitrary bp and bq. So we have like bp equal bq. That means one of the number between ap and aq divide another, as bp divides bq as their equal, and power of 2 divides each other. And that completes our proof. I hope now you can see how powerful this simple idea can be. Before I end the video, I have one problem for you to solve by yourself. Try to use Pigeonhole principle to solve this problem.